In the name of God, the most gracious, the most merciful. Praise be to God, and may prayers and peace be upon the messenger of God, our Master Muhammad, and upon all his family and companions. And now, by the declining day, indeed, mankind is in loss, except for those who have believed and done righteous deeds, and advised each other to truth, and advised each other to patience. Let's analyze a single phase to ground fault. If a ground fault occurs on phase A, meaning phase A connects to ground, current on phase A increases. Increased current on phase A means voltage there decreases. Current and voltage on unaffected phases B and C remain unchanged. Many references assume current on unaffected phases is zero. In reality, they are not zero. They remain unchanged. Phase A's current increase lowers its voltage. Phases B and C stay unchanged. Unaffected phases aren't zero. They remain constant. Meanwhile, the current and voltage on unaffected phases B and C remain unchanged. The zero assumption is relative to the fault current on phase A. With a 30 kiloampere fault on phase A, the 500 ampere current seems negligible. The voltage phase shift remains constant, while the current phase shift changes, notably due to phase A's displacement. It was assumed to be zero. When a fault current of 30 kiloamperes occurs on phase A, the current phase shift changes, especially due to phase A's displacement. Phase A was delayed by 30 degrees before the fault and approached a 90-degree angle when it happened. The difference in phase shift values and the variation in current and voltage magnitude on phase A compared to others lead to these faults being unsymmetrical. The occurrence rate of such faults, phase to ground, is 70 to 80% of total faults. Most faults in the electrical network are ground faults. The last type of unsymmetrical faults is phase-to-phase and phase-to-ground faults. Phase A was delayed by 30 degrees before the fault, reaching a 90-degree angle when it occurred. The phase shift difference, along with current and voltage variations on phase S compared to others, leads to these being unsymmetrical faults. Phase-to-ground faults occur 70-80% of the time, making them the most common in electrical networks. The last unsymmetrical faults are phase-to-phase and phase-to-ground, occurring less than 10% of the time. Analyze these faults by comparing pre- and post-fault changes. In summary, faults in electrical networks change current and voltage values. If this causes an imbalance in the three-phase system, it's an unsymmetrical fault. If balanced, it's a symmetrical fault. I will provide you with the phase diagram for this type of fault, and you need to analyze these faults by comparing the changes before and after the fault occurred. The occurrence rate of this type of fault is less than 10% of the total faults. In summary, when a fault occurs in the electrical network, there is a change in the values of currents and voltages. If this difference results in an imbalance or imbalance of the three phases, this means that this type of fault is called an unsymmetrical fault. However, if the system remains balanced after the fault occurs, these faults are called symmetrical faults. As you know, dealing with a balanced system is much easier than dealing with an unbalanced system for one reason only. A balanced system makes you able to predict its result and behavior. So when we analyze a hysteretic voltage, we analyze it through a single line diagram only on one phase only. Then we apply these results to the other phases. While dealing with an unbalanced system makes you feel like you're working with probabilities or a random sample. When analyzing an unsymmetrical fault, we find that the analysis can be somewhat complex and relatively difficult. That's why Fortescue, in his theory in 1918, decided to address this issue. He converted every three-phase unbalanced system into a balanced system. Therefore, dealing with a balanced system will be easier than dealing with an unbalanced system. This means that if I have a symmetrical fault, it will result in a balanced system, and I can handle this balanced system directly. But if it has one, then it will arise from it, and I won't be able to deal with it directly. So we first convert this to a balanced system and then analyze it. We first convert it to a balanced system and then analyze it. The idea of using Fortescue's theory is based on the fact that every unbalanced network is actually made up of three symmetrical networks, such that the sum of the three symmetrical networks will result in the same original unbalanced network These three networks include positive sequence 1, negative sequence 2, and zero sequence 0. During an asymmetrical fault, three imaginary sources appear: positive, negative, and zero sequence voltages. The zero sequence component, symbolized as 0. Networks have unique impedances: Z1 positive, Z2 negative, Z0 zero sequence. Asymmetrical faults create imaginary sources: positive, negative, zero sequence voltages. These sources and impedances cause currents: positive, negative, zero sequence. Impedance occurs with an unbalanced fault, causing imaginary sources called the positive sequence. These sources with positive, negative, and zero sequence impedances result in three currents: positive, negative, and zero sequence currents. The presence of these sources, along with the positive, negative, and zero sequence impedances, results in the flow of three currents: positive, negative, and zero sequence currents. One might ask, what exactly are these sequences and what is the difference between them? Physically, the positive sequence current mimics the normal current in the network. It has the same magnitude and rotates in the same direction as the network. Conversely, the negative sequence current has the same magnitude but rotates in the opposite direction. PSC mimics normal current, same magnitude, same direction. NSC, same magnitude, opposite direction. Normal current rightward, PSC right, NSC left. Normal current counterclockwise, PSC similar, NSC opposite. It has the same magnitude. It goes in the opposite direction. So, if the normal current is directed to the right, the positive sequence current will also go to the right, while the negative sequence current will go to the left. If the normal current rotates anti-clockwise, the positive sequence current will rotate in the same direction, but the negative sequence current will rotate in the opposite direction. The positive sequence is named as it aligns with the normal current, while the negative sequence is named as it opposes the direction of the normal current. The positive sequence will rotate clockwise, while the negative sequence will rotate in the opposite direction. The positive sequence rotates clockwise, counterclockwise, CCW in North America, anti-clockwise, ACW in Britain. The positive sequence aligns with normal current. Negative sequence opposes normal current. In the diagram, voltages are equal magnitude, angled, sequentially, CCW. Looking at positive sequence rotation, C phase A, then B, then C. For negative sequence rotation, C phase A, then C, then B. The difference is phase B and C are swapped, right? To illustrate, we use a three-phase motor. It's just like any regular three-phase system. With one difference, it rotates clockwise. If someone were to look at the direction of the positive sequence rotation in space, they would see phase A first, then phase B, and then phase C. However, if they looked at the direction of the negative sequence rotation in space, they would see phase A first, then phase C, and then phase B. This means that the difference between the positive and negative sequences is that phase B is swapped with phase C, right? To illustrate the concepts of positive sequence current or negative sequence current, we usually take a practical example, which is a three-phase motor. The positive sequence current, which perfectly matches the original or normal current, is the one that will create a magnetomotive force, MMF, that generates a flux. This flux causes the rotor to rotate counterclockwise. If you swap phase B with phase C, you will create a negative sequence current, and as a result, the rotor will rotate clockwise, which is the opposite of the original direction. We usually give an example from practical reality, which is the positive sequence current, which perfectly matches the original or normal current, is the one that will create a magnetomotive force, MMF, that generates a flux. This flux causes the rotor to rotate counterclockwise. If you swap phase B with phase C, you will create a negative sequence current, and as a result, the rotor will rotate clockwise, which is the opposite of the original direction. The process of changing the rotor's rotation from counterclockwise to clockwise does not happen instantaneously. Rather, it resists the rotor's rotation gradually, slowing it down until it reaches zero and then reverses its direction. This method is one of the ways used to perform braking on a three-phase motor, where we create a negative sequence current in the circuit by swapping phase B with phase C. So, when the rotor's speed reaches zero, we disconnect the supply from it, because when it rotates clockwise, the motor turns into a generator, and that's a dangerous situation. It always appears in the network It mimics the natural current, as we mentioned before. It shows up before a fault occurs, after a fault occurs, and also in metrical fault. It only appears in certain cases, which are there a difference in loads on the three phases. The phasor diagram shows they are equal in magnitude and direction. It indicates a component when current flows into the ground, meaning an earth fault has occurred. Zero sequence current for each phase combines to pass through a point to the neutral. Note that zero sequence current is the only symmetrical component measurable directly with a multimeter. So we measure the neutral current value and divide by 3. To summarize, it appears before and after a fault. It shows up in specific cases only where it's called this because usually the sum of the three currents at a point equals an earth fault occurred where zero sequence current for each phase combines to pass through a point to the neutral. Note that zero sequence current is the only symmetrical component measurable directly with a multimeter, so we measure the neutral current value and divide by 3. To summarize, it appears with faults, it shows up in specific cases as the sum of currents. During ground faults, neutral current is 1/3 zero sequence, I0 is I neutral 3, or I neutral is 3 times I0. It only appears in certain cases. It is the current at the 0 point, and during ground faults, neutral current equals 1/3 of the zero sequence current. Thus, I0 equals I neutral divided by 3, or I neutral equals 3 times I0. So it is the current that flows at the 0 point, and the neutral current that arises during ground faults equals 1/3 of the zero sequence current. Therefore, I0 sequence equals I neutral divided by 3, or we can say that I neutral equals 3 times I0. Any nutri is equal to 3, or we say that any nutri is equal to 3. Any note, any n. Therefore, earth fault protection is called zero sequence protection by some manufacturing companies to protect against zero sequence currents that will arise due to the ground fault. The asymmetrical components equation can be expressed using a specific matrix. Follow along with me to analyze this matrix. This matrix helps us in deducing the value of the sequence current from knowing the phase current. Or, deducing a value from knowing, we denote it with a symbol, and we denote it with a symbol. While it is, the way to write this matrix is as follows, where we start with what we want to deduce first. So we say I0, I1, I2, I0, I1, I2, 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 I1, I2, I2, I1, I2, I2, I3, I0, I1, I2, I2, I1, I1, I2, and it equals 1/3. We open a new matrix and place here 1, 1, 1, 1, 1, A, A2, A2, multiplied by another matrix, IA, IB, IC. To find the value of zero sequence current, we multiply this matrix by that matrix. It is known that a matrix consists of rows and columns. I0, I1, I2, I1, I2 equals 1/3. Open a new matrix, 1, 1, 1, 1, 1, A, A2, A2, multiplied by IA, IB, IC. To find zero sequence current, multiply these matrices. A matrix has rows and columns. This matrix is 3k3, and the second is 3k1. For matrix multiplication, the first matrix's columns must match the second's rows. Multiply by dropping the column onto each row. I0 sequence, I positive sequence, I negative sequence, zero sequence, current, I0 sequence equals 1/3. The matrix is described by the number of rows and columns it has. This matrix consists of 3 rows and 3 columns as shown in the figure and is called a 3A3 matrix. The second matrix consists of 3 rows and only 1 column, so we refer to it as a 3A1 matrix. It is well known from the rules of matrix multiplication that to multiply 2 matrices together, the number of columns in the first matrix must match the number of rows in the second matrix. This means that the 2 numbers that are close to each other must be the same, and the result of the multiplication will be the 2 numbers that are far apart. The multiplication is done by taking this column and dropping it onto the first row to find I0 sequence, then dropping it onto the second row to find I positive sequence, and then dropping it onto the third row to find I negative sequence. Thus, the value of zero sequence current is as follows. I0 sequence equals 1/3. It equals 1/3 multiplied by 1 times IA plus 1 times IB plus 1 times IC. As for the value, I1 equals 1/3 multiplied by 1 times IA plus A times IB plus A squared times IC. As for I2, it equals 1/3 times 1 times IA plus 1/3 multiplied by 1 times. As for the, so it will be 1 to 3 times 1 in a squared times. In IB plus A times IC, put A, then A squared, and put A squared, then A. The operator A, 1 at 120 degrees, while its bottom 1 at 240 degrees. Squaring. Doubles angle, squares magnitude. What applies to the current matrix also applies to the voltage matrix. Write matrix V0, V1, V2, out 1/3, open parenthesis, matrix. And what applies to the current matrix also applies to the voltage matrix. Now, let's take the following example. If the voltage on phase A equals 120 at an angle of 0, the voltage on phase B equals 120 at an angle of 120, and the voltage on phase C equals 120 at an angle of 120. So, what is the value? First, we write the matrix V0, V1, V2 equals 1/3. We open a parenthesis or a matrix. At the beginning, we write the matrix V0, V1, V2 equals 1/3. We open a matrix, and we open a matrix, and we open a matrix. 1, 1, 1, 1, 1, A squared multiplied by VA, VB, VC. Therefore, the value equals 1/3 multiplied by VA plus VB plus VC. Thus, it equals 1/3 multiplied by 120 at an angle of 0 plus 120 at an angle of 120 plus 120 at an angle of 120. 1/3 multiplied by... and 1/3 multiplied by 120 at an angle of 0 plus 120 at an angle of 120 plus 120 at an angle of 120. The inspiring revival of a nation. The system is balanced because the voltage value is constant across the three phases, 120, 120, 120. Secondly, the phase shift between each phase and the one following it is fixed at 120 degrees. Its rotation is counterclockwise, matching the original voltage. The yellow phase angle shows counterclockwise rotation. If the yellow phase angle is 120 or 240 degrees, rotation is counterclockwise. If it is 120 degrees, rotation is clockwise. Regardless of rotation direction, the system stays balanced. Being balanced, the three voltages cancel at the neutral point. Thus, their sum at the neutral point, V neutral, is 0. If the angle of the yellow phase is 120 or 240 degrees, then the direction of rotation will be counterclockwise. If the yellow phase has an angle of 120 degrees, then the direction of rotation will be clockwise. Regardless of whether the rotation of this phasor diagram is clockwise or counterclockwise, this system remains balanced. In a balanced system, three voltages cancel at the neutral point, making V neutral 0. The zero sequence voltage is also 0. The positive sequence voltage is 1/3 of VA plus AVB plus A2 VC. At the neutral point, V neutral equals 0. The zero sequence voltage is V neutral divided by 3, which is 0. In a balanced system, the zero sequence is 0. The positive sequence voltage is 1/3 of VA plus AVB plus A2 VC. The budget and sequence voltage is also 1/3 of VA plus AVB plus A2 VC. So it equals 1/3 times 120 at angle 0 plus 1 at angle 120, multiplied by 120 at angle 240, or minus 120 plus 1 at angle 240, multiplied by 120 at angle 120. At 120, at an angle of 120, phasor multiplication means multiplying magnitudes and adding angles. The positive sequence voltage is 120 at angle 0, confirming it represents the original voltage. The negative sequence voltage is anticipated, island, plus 120 in the corner, equals 3. 360 at angle 0 divided by 3 equals 120 at angle 0. From this, we conclude that the positive sequence voltage only represents the original natural voltage. As for the negative sequence voltage, we expect its value before performing any calculations. Here it shows us that its value also equals 0, because it only appears in certain cases, as we mentioned before. Since this example shows us that this means that its value will be 0. To prove this, follow along with this example where the value equals 1/3 multiplied by, so equals 1/3 multiplied by B. Multiplying phasors involves adding angles. In a balanced system, V2 is 0 because the vector sum is 0. This is a known result. Angle 240 times 120 at angle 120 plus 1 at angle 120 times 120 at angle 120. Add angles when multiplying phasors. V2 is 1/3 of 120 at angle 0 plus 120 at angle 120 plus 120 at angle 120. In a balanced system, the vector sum, so V2 equals 1/3 times 120 times angle 0 plus 120 times angle 120 plus 120 times angle minus 120. And since this is a balanced system, this means that its vector sum equals 0. And therefore, V2 equals 0 over 3 and equals 0. And this result is known in advance. Given the values of the positive sequence, negative sequence, and zero sequence for current or voltage, can phase voltages be deduced? Use this matrix to find IA, IB, IC. Use a 3x3 matrix. First row, 1, 1, 1. Swap A2 with A. Here, A2 and A, multiplied by I0, I1, I2. Symmetrical component helps identify fault type via positive, negative, zero sequences without knowing fault current. If only positive sequence is present, it indicates a symmetrical fault. Once upon a time in a land far away, there was a story that began with a single word. So here it is A2, here it is A2, here it is A, and here it is A, multiplied by I0, I1, I2. The main benefit of the symmetrical component is to know the type of fault through positive sequence, negative sequence, and zero sequence without having to know the fault current at all. If the fault only contains positive sequence, this is evidence that this fault is of the symmetrical fault type. But if it only contains this, it indicates that this fault. If it contains this, it means that the fault and the ground are part of the fault. The zero sequence means that the fault is related to the voltage, and the ground is part of the fault. The revival of a nation